Dear students, welcome to the second part of the module 1, Introduction to Kinematics of Machines. So in this session, we will discuss about mobility of a mechanism, and then we will see how to calculate the degrees of freedom of a mechanism. So let us first understand what is meant by mobility of a mechanism. Mobility of a mechanism is the number of degrees of freedom with which a mechanism may move. Now here in this definition, you see an important terminology which is called as degrees of freedom. Now let us understand what is meant by degree of freedom of a mechanism. So in general, degree of freedom, if you remember your basic courses of mechanics, it is simply defined as the number of independent coordinates required to specify the motion of a rigid body. Now let us see how can we apply this definition in context to a mechanism. So for a mechanism, the degrees of freedom, it can be defined as the number of independent coordinates required to describe the configuration or position of all the links of the mechanism with respect to the fixed link at any given instant of time. Alternatively, you can define degree of freedom as the number of independent coordinates required to specify the motion of all the links in the mechanism. Let us understand this definition further. If you see, let us take an arbitrary mechanism here, right? Let us see this diagram. Let's consider this link as link 1. Now let us assume this link as input link. Now let's assume that this input link, it rotates through an angle of theta. Now let us consider this link as link 2. Now when the link 1, it rotates through an angle theta, the link 2, let us assume it rotates through a certain angle beta. In the same way, let's assume this link as link 3, and let us again assume that this link 3, it rotates through a certain angle phi. Now if the motion beta and theta, they can be expressed in terms of the motion of the input link theta. So let's say if we say beta is a function of theta, phi is also a function of theta, then only one coordinate, that is the theta coordinate, will be sufficient to describe the motion of the links 2 and 3. And let us generalize this to other links also. Let's say link 4, then link 5. So in this case, we can say that only one coordinate is required to define the motion of remaining links 2, 3, 4 and 5 in the mechanism. So we can say the degree of freedom of this mechanism is 1. Now let us consider the same mechanism again, right? Now let us say this is my input link, link 1, right? Let us assume that this is again input link, right? And again we are giving a motion of theta to this input link. Now let us consider this link 2 again as another input link, and now we are giving a motion of, let's say, beta to this link. Now let us consider this link 3, 4 and 5 as the remaining links, and let us say the motion of these links, it is defined by angles gamma, then let's say angle psi, and then you can, let's say this angle as alpha. Now if the motion of remaining links, that is link 3, 4 and 5, they are defined with respect to the motion of links 1 and 2, right? So let us generalize this further. That means if we say that the variable gamma, it should be a function of both beta and theta. The variable psi, which is defining the motion of link 4, it should be a function of again both beta and theta. And then the variable alpha, if we say again this is a function of beta and theta. So in this case we can say that two coordinates, that is theta and beta, they are required to specify the motion of the remaining links 3, 4 and 5 in the mechanism. So in this case, we can say the degree of freedom of this mechanism is 2. Now, you can see here this angles gamma, psi, alpha, they are actually defining the position of links 3, 4 and 5 with respect to the fixed link, which you can see here. Now let us move ahead and let's see this. Before directly jumping to the calculation of degree of freedom of a mechanism, we will first see what is the degree of freedom for a kinematic pair. So now we will consider all the kinematic pairs one by one, and then we will see how can we actually define the degrees of freedom for these kinematic pairs. So the first pair which you see here in this diagram, it is called as sliding pair. Now in this diagram, you know that this rectangular bar, it can be considered as link 1. Then this rectangular hole, it can be considered as link 2. Now we can say that link 1, it is translating relative to link 2. So now only one coordinate, let us assume that coordinate as delta S coordinate, it is sufficient to define the relative motion between the two links 1 and 2. So in this case, we can say the degree of freedom of this kinematic pair is equal to 1. Now let us take another example. In this example, again you can see here, if you consider this collared shaft as link 1 and this hollow cylinder as link 2, then you can say that this link 1, it is executing a rotating motion relative to link 2. Again, in this case, the motion of the link 1 relative to link 2, it can be defined by only one coordinate, which is the delta theta coordinate. So again, the degree of freedom for this revolute pair, it will be equal to 1. Now let us consider the screw pair here. So in a screw pair, as we know, when this screw, right, which is defined as link 1, it is going to turn, then this nut which is defined as link 2, it is going to travel through a certain distance. Now in this case, we can again define two coordinates, one for the translation of the nut. So this coordinate, let us say this coordinate is delta S, and one for the rotation of the screw. So let us say this coordinate is delta theta. Now in this case, as we have already seen in the previous sessions, that this delta S and delta theta, they are related by this relation. So if you see here, the two coordinates delta S and delta theta, they are interrelated to each other. So we will say that the degree of freedom for a screw pair, it will be equal to 1, because the definition of degree of freedom, it mentions that the coordinates which are required to specify the motion, they should be independent of each other. So in this case, we are seeing that delta S and delta theta are not independent of each other. So therefore, we will conclude that the degree of freedom for a screw pair is equal to 1. Now let us take this example of a rolling pair. Now in a rolling pair, you can see here, this is a wheel which can be considered as link 1. Now this wheel, let us assume that this is rolling on a flat surface. So this flat surface, it can be considered as link 2. Now to define the relative motion between link 1 and 2, only one coordinate is sufficient, which is delta theta coordinate. So now the degree of freedom for a rolling pair, it can be taken as 1. Now here there is a small twist. If this motion is pure rolling motion, then in that case the degree of freedom for this kinematic pair will be equal to 1. But let us say that this motion is not a pure rolling motion. That means in addition to the rotation delta theta, right, this wheel is also sliding. with respect to link 2. So that means you again have a translatory coordinate delta s. That means that this wheel is skidding relative to the flat surface. So in that case, you will say that the degree of freedom of this rolling pair is equal to 2. Now let us take the example of a cylindrical pair. Now in this cylindrical pair, if you observe, there is a solid cylinder which is rotating inside a hollow cylinder. So let us consider this solid cylinder as link 1 and let us consider this hollow cylinder as link 2. Now you can see here, in this case, there will be two coordinates which will be required to define the relative motion between the links 1 and 2. So one coordinate will be the rotational coordinate, that is the link 1, it is rotating relative to link 2. And another coordinate, it will be the translatory coordinate delta s. That means link 1, it can also slide relative to link 2. So in this case, we will say that the degree of freedom of a cylindrical pair is equal to 2. Now here in this case, just note down the difference between a screw pair and a cylindrical pair. In both the cases, if you observe, the motion is happening in two directions, that is delta s and delta theta. But still we will say that the degree of freedom of a cylindrical pair is 2 because here the two coordinates delta s and delta theta, they are independent of each other. Now let's see the example of a spherical joint. Now here you can see a ball and socket joint. Now to establish the degree of freedom of a ball and socket joint, let us assume a three-dimensional Cartesian coordinate system such that one of its axis, it is aligned with the axis of ball. Now the motion of the ball, it can be defined as a rotation about this z-axis, then another rotation about this x-axis, and then another rotation about this y-axis. So basically three coordinates delta theta, delta beta, delta gamma, they are required to specify the motion of ball in the socket. So the degree of freedom of a ball and socket joint, it is equal to 3. Now here you can see that a rectangular bar, let us say this is link 1, it is resting on another rectangular bar. This kind of arrangement is referred to as planar kinematic pair. Now in this case you can see here again, if we consider a three-dimensional Cartesian coordinate system, so you can easily see here that this link 1, it can rotate relative to this link 2 about this vertical axis, and at the same time it can perform translatory motion along the x and z direction. So the degree of freedom for a planar pair, it is equal to 3. Now let us see the example of a higher pair. So as you can see here, the wheel rolling on a flat surface is also an example of higher pair. Now it is very important to note down here that the previous kinematic pairs which you see here, that is the sliding pair, the revolute pair, the screw pair, the cylindrical pair, the ball and socket pair, as well as the planar pair, they are all examples of lower pairs. That means in all these cases, the two links, they are having a surface or area contact between them. However, if you see the case of a rolling pair, generally it is an example of higher pair. Now let us see the degree of freedom of a higher pair. So as we discussed before, this wheel, it can turn around its own axis. So one coordinate that will be required to define the motion of this wheel, it will be delta theta. Another coordinate that will be required to define the motion of this wheel will be delta s, considering that this wheel is slipping relative to the flat surface. So here the degree of freedom of a higher pair is taken as 2. So with this, I would like to conclude this session, and in the next session, we will see how can we calculate the degree of freedom for a mechanism. Thank you.